Good. We have these beautiful tools, the representations, the representation PKJM of SL2C, and this map Y gamma that sends a representation of SU2 in representations of in gamma J JM representation of SL2C. And let's put it there. This map implements, in some sense, K equal gamma L. Let's put it there. And think about BF theory. So say you have an action which depends on a two-form B and a generic connection omega. This is the action. This is a very simple theory where this is some group G. I don't want to say which group it is. And I want to do the quantum theory of this action. Now, the quantum theory of this action, it's very simple because, as I said, this action is topological. The equation of motion is this flat curvature and covariantly constant two-form B, which means that there are no local degrees of freedom because everything is rigid locally. But nevertheless, if the manifold which is defined is non-trivial, there are degrees of freedom, or if there's a boundary, there's degrees of freedom. So let's just rapidly see how this can be defined. I have the way of doing. I want to define a path integral for that. Some dB d omega e to the action I h bar over this action BF. In some sense, okay, they want to give meaning to this thing here. And the way I want to define it is the way Feynman defined path integrals to start with in his PhD thesis. So the one of you who are doing a PhD thesis, remember that in his PhD thesis, Feynman rewrote quantum mechanics with path integrals. So you don't get discouraged. So what he did is in field theory, in one dimension, to take time, discretize it, and just write little transition amplitudes step by step, and then rewrite this the resolution of the identity in the middle of single integrals. So you have a multiple integral, which somehow formally in the limit becomes a path integral. So I want to do something like that. I want to discretize and write a multiple integral. And like Feynman, take this as a definition of this thing here, which otherwise is not well defined. So let me discretize these fields. This is my four-dimensional space for the manifold, on which these fields are defined, these continuous fields are defined. And to discretize them, I do a triangulation. And I write the fields as on a triangulation. Why a triangulation? Because what you do in lattice QCD when you want to do the same thing in lattice QCD, you want to discretize a functional integral, you discretize it with a cubic lattice. But the cubic lattice is nicely cubic because you have a metric, background metric, which tells you what it means to be cubic. Here, you don't have a background metric. So you do the most covariant things you can. So you discretize it by breaking this in simplices. But this is four-dimensional. So a four-dimensional simplex is not a tetrahedron. It's a object with one extra vertex, which is a five-simplex. Sorry, four-simplex. A four-simplex is is a tetrahedron with an extra point joined by, okay? Which in space-time, imagine you have a tetrahedron sitting here, and in space-time it shrinks to a point. And what it cuts out from space-time, it's exactly a four simplex. It is bounded by the original tetrahedron, and each face goes to a point, so it's bounded by 1 plus 4 tetrahedra. So this four simplex is bounded by 4 tetrahedra, and you break this in four simplexes, and so on and so forth. And of course, as we did in 3 dimensions, it's much easier to go to the dual to think about that. So to put a point here, and the four simplex represented as a vertex, and the 5 tetrahedra around represent as 5 edges. So a tetrahedron, which is a 3-dimensional thing, now correspond to an edge. It's a tetrahedron. And the triangles bounding the tetrahedra here, the triangle, correspond to, in the dual. So you see, when you have a triangle here, you can go to this tetrahedron, this tetrahedron, this tetrahedron, this tetrahedron, and make a tour around it. So it's like following this edge, this edge, this edge, this edge, this edge. You can imagine there is a face here. So a triangle corresponds to a face. So in the dual of the triangulation, you have vertices, edges, and faces, and you can imagine a bubble thing. So you have these surfaces join on edges, and the edge in turns join in point. This is called a two-complex. So faces, edges, and vertices make something which is a two-complex. Abstractly, a two-complex is a graph plus a definition of faces, which are closed curves along links. Okay? Now, each B field, the B field is a two-form. So to discretize a two-form, you naturally integrate it on a triangle. So to each triangle, which means to each face, you can associate a discrete version of B. And a connection is a one form, so you can naturally integrate connection along lines. And the obvious way is integrate along these lines. This is a connection that goes from the center of this four simplex to the center of this four simplex. So it's associated to the tetrahedron. And in the two complex is this line. So you integrate the connection along this line. You go, if you want, from this reference frame to this reference frame if you think for gravity. So B field, the continuous B fields goes into something integrated on faces, and the connection goes something integrated on edges. Of course, when you integrate the connection, you don't want to integrate just the one form because its value in the algebra of the group. What you're doing is the exponentiation of it. So what you really want to do is to define a group element. Let me call it G generically. I'm not saying in which group I am, which is the integral along the edge of the connection, while this is the integral on the face of the two form. This has a value in the algebra, this has a value in the group. Okay? So I'm just doing a discretization of the space-time, and of course the continuous field theory is truncated because I am replacing continuous field with discrete field. I'm doing exactly what people does in lattice QCD, except in a little bit more covariant manner. You will see that this little bit covariant manner will have a dramatic consequence in differences with lattice QCD, which I will probably not have time to discuss today, but I'll discuss tomorrow. Okay? Once I've done that, I can rewrite this as an integral in dB, whatever it means, an integral in the group element on the group G, where this is on all the edges and this is on all the faces, and here I have some dual thing, sum of all the faces, but here I have the curvature. So how do I discretize the curvature? Well, it's pretty obvious, because I have a connection defined on these edges. The curvature is the limit of the holonomy of a connection when you have something small. So to discretize, you just take the group element here, the group element here, the group element here, the group element here, you group element here, and you make the product. And this, of course, it's a measure of the curvature inside. If there is no curvature, you get the identity. If there's curvature, you get something different for the identity. I'm just motivating a formula which I'm going to write in a moment. So here I'm going to sum over the faces, some B associated to the face, and some product of group elements sitting on the edge around this face. I write this E in F, all the edges around the face of the group element there. And then I can do the B integral, at least formally, and finally end up to an expression which is actually well defined, and it's very simple, by noticing that this is the integral, this is of the kind, the integral dp eipx is proportional to delta of x up to some 2 pi or something like that. So this is going to be, when I do these integrals, 0 unless this is unless this is 0. So now I can write, and finally I get something well defined. The integral on the group element associated to the edges, integrated on one copy of G per each edge, of the product on the faces of delta on the group of GE1, GEN, where these are the E's on this face here. And this is actually a well-defined expression. If the group is compact, this is well defined. If the group is non-compact, I might get some infinite here, but I'll deal with that in a moment. I don't want to think for a moment that the group is compact. So this is a number, which actually depends only on the triangulation. And if you go think for a moment, it only depends on the topology of the manifold, how the manifold is it's connected, because there's nothing else to depend from, so it depends on the manifold here. I can slightly write this in a little bit different manner, which is going to be, so that's I take as a definition of a discretized path integral. I'm going to rewrite it in a slightly different manner, which is going to be used in a moment. So let's look at one of these faces. Remember, the face is dual to a triangle. So let's look at one of these faces. So I have a group element here, E, group element here, a group element here, a group element here. And I'm going to do a little bit of cosmetic, which is going to be useful in the following. This, by the way, is how the Ponzano-Regges model is defined, how BF theory discrete is defined. I mean, there's a lot of... If you want, this is just a discretization of the integral on all possible connections of all flat connections. Delta on flat connections, the volume of the flat connections sitting on a manifold. Ed Witten has worked with that, doing some mathematics with that, things like that. Just in parentheses.
To have the path integral for the full theory, you should do some limit.
No, because this turned out to be independent of the triangulation. You can prove that this is independent of the triangulation. Yeah, if you refine the triangulation, if you do put the eyes on the and take away the volume of the group appropriately, this is independent of the triangulation. Which is not going to be true in general relativity, because then the truncation will be an actual physical truncation. Here the truncation turned out to be irrelevant. Okay, so what do I want to do? First, let me double the variables because it's convenient. So let me introduce variables. This is a vertex. Let me introduce variable g vertex edge. So this is edge 1. This is edge 2. So this will be vertex edge 1. Here will be g vertex edge 2. And I can just rewrite this as an integral in dg EV. So all this twice as many variables. And then the same thing, product on the face, delta, and now I have g v e1, g minus 1 e1, v2, g v2, and so on and so forth. So let me just write the product around the face of the GEV appropriately. And then I want to introduce group elements here. It's just cosmetic, but it's going to be very useful to do the relativity one. So I want to have a group element here, which I call H vertex face. Vertex face. H, this vertex here, v tilde face, and so on. So this is a face. Okay? And I want to rewrite this as the product on this DH vertex face, the product of this, where I trade these two for this. So I write delta, the product on the faces of just delta of H F vertex 1 F vertex n. So I want this to be the product of this delta, so to be 1, and then I want this to be given by this time this. So the product on for each couple vertex face of delta H vertex face GE GE prime, where GE E prime are this and that. Okay? Which allows me to get to the form that I need, which is the following. And you will see why I like it, because now I have the products of all vertices and all faces, so I can collect all the vertices. So I can write this as an integral EH vertex faces delta H a product on the faces of delta h face vertex 1, h vertex n. So I go around for each face I go around and put a delta, and then I have all these. So I have the product on the vertices. Let me separate it. Some vertex amplitude, and the vertex amplitude is what? Is I have to integrate over the. I have also to integrate over the g e v also, of course. So the a vertex is an integral on the g. This g, and all the other that come from the other faces. So it's an integral of dg, which depend on a vertex and an edge of the product on the faces that are adjacent to this vertex. So this vertex here has this phase, but there will be also the others. Delta g h vertex face g e prime, where by e prime I mean the one sitting inside there. So that's I've just done some juggling. It's the same formula as before, written in a different manner. Okay, and if the group is compact, this is a well-defined expression, which you can view as a partition function, the path integral of BF theory. Now, why I've done all this juggling? Because a delta function on a group, this is true, think about SL2C, but it's true for any compact group, delta function of the group can be written as a sum on the representations that do it for SU2 of 2j plus 1, the dimension, and then the trace in the j representation of g. This is a formula that is true for all compact groups, and if you think of U1, this is expression of a delta of a sum of E, I, N, X, and phi on a group. So let me write this here. Instead of a delta, I write sum over the representation of trace in the representation J. And now I want to take this and interpret it for a theory where the group is SL2C, but on the boundaries I have SU2 imposed by K equal gamma L. So how do I do it? Well, each vertex, remember, each vertex is a four simplex. So it's this thing here. This is the amplitude of the four simplex, which depend on this boundary group elements here, which sits on its boundary. So its boundary is a three-dimensional surface, which is triangulated. And on the boundary, I have, let's view in this way, I have the vertex, I have the edges, and on the boundary, I have five. If I cut here, I have a graph where I have nodes and links. So I have a spin network on the boundary. I have a four-dimensional region of space-time with a three-dimensional boundary, which is discretized, is discretized with tetrahedra. At each tetrahedron I can represent as a node. The way the tetrahedra are put together it gives links. So I have a spin network. The spin network being this spin network here. Okay, with 10 links and 5 nodes, 5 tetrahedra attached to one another, and 10 faces, which are the boundary of a fourth simplex. Okay, so on the boundary, I want the quantum states of gravity, which are SU2 states. But on the bulk, I want the full SL2C invariance of the theory. This object here is a function I'm integrating on the group G, is just a function of the H. A vertex is just a function of the H, of the 10H that sits on each boundary, that sits on these links here. This H is here. Okay? So it's pretty obvious what I have to do. I have to interpret this as the SU2 elements that define the quantum geometry on the boundary, but keep the SL2C in the bulk. Generativity is SL2C in the bulk and SU2 in the boundary. So I want this H here to be in SU2, but I want this G here to be in SL2C. That's what I want. Or if you want, I want to have an SL2C theory, but on the boundary, I want to be able to sit on a boundary, be on the time gauge, and represent my states as SU2. So I'm almost done up to a detail. So Z is the integral of these H things, which are SU2. This is a product, this is a set of SU2 element, delta, I know exactly what it means. This is a product of SL2C things, I know exactly what it means. How is it defined? Is it defined by integrated over SL2C? Okay, what? A product of the faces of the trace J, remember these are SU2, so this is the spins of SU2. But here I have SL2C element. So I need a way now to map this SL2C element into SU2. I have it. That's exactly Y gamma. If you want, I am in the representation J. But I know this I have matrix elements in unitary representation of SL2C, but I just put Y gamma here and here, Y gamma and Y gamma. One is a dagger, so let's see. This is the good one, SU2 to SL2C, and this is its inverse. And I'm done. This is the amplitude of loop quantum gravity. Let me write it just a little bit more explicit so you can see it. I don't need this anymore. That term, you see that there's actually a well-defined object. It's hard to compute with. So trace J of some H BF and some GE prime with a Y dagger here and a Y here. What it means is that I take the representation element. This is SL2C. So it is a PK here, but I'm mapping Y maps to gamma JJ. Okay? And here I have JM, JM prime. KM, KM prime, but the Y maps K to J. So JM, JM prime. Okay? And I have another one where I can just put it inside. GE, GE prime. And here I have the Wigner matrix J of H m prime m. And that's summing. This is a product, and the trace is summing the other one. So this is what the notation means. So if you were confused about this notation, this is explicit. In terms of a representation matrix, this is Wigner representation matrices, and this is the SL2C unitaries. Okay? So if you have a book telling you explicitly this one, this is just a number. And you have to integrate of SL2C, you integrate of SU2, and you get the partition function. Now, we don't want the partition function, we want transition amplitude. So what is the story about transition amplitude? Well, if this four-dimensional piece of space-time that I mentioned has a boundary, which is what I want, the four simplex, some four simplex sitting here are bounded. Let me just draw, not try to do four-dimensionally, have a because I'm going to die, bounded by one tetrahedron of these four simplex sit in the boundary. Right? So this means that one of these nodes sit in the boundary, and maybe there is another one here, and there's another node, and there's a link here between the two. So I have a spin network on the boundary, and when I do these deltas on some, so if this is a link on the boundary, when I have a face, an inside face, which is on the boundary, some of these actually sit on the boundary. And these I'm not integrating over, so this will be on the H, on the links on the boundary, which stay out. So I'm only integrated on the edges, which are the inside edges, and not on the boundary edges. So I get this formula gives me something which depends on the SU2 element of the boundary. So I have, for each boundary link, I have the corresponding SU2 element, which means that this is actually a function in L2 of SU2 to the L, where L is the number of link, the total number of link, or if you want, in the tensor product of SU2 to the L upstairs times SU2 to the L downstairs. So this is an element in the Hilbert space, which is the Hilbert space upstairs tensor the Hilbert space downstairs, which is what I call the boundary in Hilbert space. And since it is a Hilbert space, an element here is also a bra, is also a ket. So a ket is also a bra, so this is a bra. So this is something that given any state here and any state here, I can contract with the state here and there, and give me an amplitude. Right? So now I have an explicit way. If I have one of the spin network states here, or any combination of spin networks here, a quantum state of geometry here, a quantum state of geometry here, I can compute a map from one to the other. I mean, I can sandwich this with the two states. I get a complex number, which is the amplitude of going from here to here. Is that the final amplitude of loop quantum gravity? Well, this depends on the triangulation. I've chosen a triangulation in between, and this is a truncation. So let's remember that this depends on a triangulation. Let's put a little delta here, remember, it's a triangulation. So if the gods are good, when you refine the triangulation, this thing converges to a number which does not depend anymore on the triangulation, which is what happened in QCD. Right? In QCD, if you refine your lattice, the amplitudes, which you can also do in QSD, in QCD transition amplitude from the past to the future, when you refine your lattice, the result converges to a number. So this is a truncated LQG amplitude. The exact LQG amplitudes are defined a little bit abstractly as the value of this when you refine the triangulation. Concretely, all calculations that have been done in this formalism are for a fixed value of for a fixed triangulation, in fact for rough triangulations, and little is known about the actual convergence when you refine the triangulation. I mean, there are hints and suggestions that the thing should, and reason to believe that the actual number is independent of the triangulation, but no solid results so far. Where there are solid results so far is that this very abstract formula, which seems to have nothing to do with Einstein equations, after all, I got this in a very indirect way, right? I just said, well, Einstein equations BF plus K equal gamma L, let's do quantum BF and sort of let's squeeze in K is gamma L, and you say, I mean, come on, I mean, do you have any hope that this turn out to be related to classical GR? Well, the answer is yes. And in fact, there are theorems, there's a number of theorems that says that in a suitable limit, this gives the, in appropriate sense, with a lot of caveats, this gives the Hamilton function of general relativity. So this will require a full lecture to specify all the caveats and in which sense and what is here and what is not there. But there's a number of theorems that says that inside here, there are the Einstein equations. It's written the Einstein equation inside. What is missing? A few details. One is that for each vertex, in the vertex amplitude, there are 5 SL2C integrations, right? Because its vertex has 5 edges coming out. If you study this expression here, you discover two things. That one, after you integrate over 4 SL2C element, the result is independent of the fifth SL2C element, which means that the last result is a little bit redundant. It's just because of the gauge invariant here. If you gauge transform all the four, you get the same result. But also means that if you integrate on all the 5, you have an integral of the group of you have an integral dg over SL2C, which is equal to infinity, of course, because this is the Hahn measure of a non-compact group, which is infinite. So this is easy to correct. You just, for each vertex, integrate on 4 of them and not 5 of them. And it doesn't depend on which 4, and the result is immediately invariant under the change of the fifth of them. So this makes it finite. At the beginning it was confusing, and then I guess the Polish people cleaned this up. These expressions here are finite and ultraviolet, in a sense because there's no ultraviolet, right? This is like doing the path integral of the geometry inside, but the geometry is never too small inside. Nevertheless, there can be some infrared divergences because you're summing of all geometries, so there are, even if you have a fixed boundary, the geometry inside can be arbitrarily big. So there are these big geometries contributions, which might give divergences here, and there is a chapter about this in the book. I'm not going to discuss much them. The version of the theory with cosmological constant make these divergences finite, because bounds, the divergences come from this sum of a j spins that goes to infinity. With the cosmological constant, this goes to a maximal j and is finite. I'm not going into that. I'm just mentioning it. So this equation here, with this equation here, which is made explicit here, is the definition of the transition amplitudes of loop quantum gravity in the covariant formalism. What I'm going to do in the next lecture is to give you some details about that more, and give you some intuition of what is actually happening here, and explain in which sense this is very similar to QCD, in which you do a discretization on a lattice and you define the theory there, and that's how people compute the masses of proton. First, the best computation of mass of proton is it's in a truncated theory on a finite lattice. And I will tell you how much similar it is to lattice QCD and how much different it is from lattice QCD. There's a dramatic difference. The dramatic difference is in lattice QCD you have a parameter. You have a similar expression with a parameter that you have to take to 0 and to a critical point. There's nothing like that here. This is shocking at first to anybody who does discretization and you see, there's no parameter here. It's just groups, integrals of groups and maps. So where is the scaling limit here? Like in QCD, you have to take A to 0. It's not. Why? How is it possible? I will explain that I will give you a convincing answer to this question. It's the actual manifestation of the diffeomorphism invariant of general relativity in this context. When you discretize a theory on a metric manifold or on Newtonian time, you have a parameter to take infinity. When you discretize a theory properly in a manifold without metric, you don't. It's just automatic. But in a sense, I've given you the full loop quantum gravity in the covariant formalism so far. The rest is commenting that, understanding that, and then of course extracting physics out of that. Because out of these formulas, we want to compute what happened in the early universe, what happened with black hole when it explodes and bounces, what happened in the physical regime where general relativity goes wrong. Here are the basic equations. And I stop here. Thank you.